Welcome to the AP Physics Magnetism Review. We're going to start this with permanent magnets, the kind of magnet that you might have played with when you were a child. A magnet has a magnetic field surrounding it. We usually call magnetic fields B fields. And that B field, you should memorize this picture. It's away from the north, then it loops around to the south. Every permanent magnet has a north and a south pole, or in other words, a dipole. Opposite poles attract, likes repel. Now the Earth, the North Pole, up where Santa Claus lives, is actually a south magnetic pole, and the South Pole, where the penguins live, is actually a north magnetic pole. So the geographic poles and the magnetic poles of the Earth are switched from what you might think. Go ahead and try this next question. Pause your video now. Okay, you should have tried this question. It says 2 bar magnets are to be cut in half along the dotted line shown. None of the pieces are rotated. After the cut, what happens? So let's first look at the top magnet. When we cut this in half, here's the north, here's the south. There's no such thing as a magnetic monopole. So this half will regenerate a south, and this half will regenerate a north. If we cut this one long ways, well, they both still have a north on the left, just thinner, and they both have a south on the right. And this is asking what will happen. So none of the halves will attract. Well, I can see that these will definitely attract, so that's false. The 2 halves of each magnet will attract each other. Well, this one down here, 2 souths repel and 2 norths repel. So no, they're not all going to attract. 2 halves will repel. No, these are attracting. 2 halves of the top magnet will repel. No. 2 halves of the top magnet will attract, and the 2 on the bottom will repel. Choice E. Okay. Now, when a charge is moving through a magnetic field, so a charge, it could be a little positive charge or it could be a little negative charge. Anytime it moves through a magnetic field, it feels a magnetic force. There's only 2 exceptions. Number 1 is if it's actually not moving, it's stationary. So if the velocity is 0, the magnetic force is 0. The other exception is if the charge is moving parallel to the magnetic field. So say you have your little positive charge, it's moving to the right, and it's in a magnetic field that's pointing to the left. It would feel 0 force because these are parallel. The velocity and the field are parallel. But as long as it's not those 2 cases, you can find the direction of the force using right-hand rule number 1. You point your fingers in the direction of the motion. You curl your forefingers in the direction of the magnetic field, and your thumb points in the direction of the force. Now, one important thing to remember is that the force, the magnetic field, and the velocity are always perpendicular to each other. So I think I can try and show you that. So that if the velocity is my blue marker and the magnetic field is my green marker, so they're perpendicular to each other, then the force is perpendicular to the other 2. So it's coming towards you in this picture. Okay? They're always perpendicular to each other. So we use the right-hand rule number 1 to figure out the direction. Now note that this only works for positive charges. If you have a negative charge, either take the opposite direction or just use your left hand. Here's the equation that we would apply for magnetic force. Now when charges go into magnetic fields, they get forced into a circular path. And so often in problems we will set the magnetic force equal to the centripetal force. And one little easy trick, easy point that you'll probably see on your AP test is a question that says, how much work does the magnetic force do? Well, the magnetic force does 0 work because it's always perpendicular to the velocity. Go ahead and try the next problem. Pause your video now. Okay, a positively charged particle moves to the right and enters an electric field directed to the top of the page. In which direction does the magnetic field have to point in this region so that the particle goes straight through? So we know that charges, positive charges, get forced in the same direction as electric fields. So I have an electric force going up, and it's equal to QE. The only way that this charge will go in a straight path is if I have a downward magnetic force, Fm, which is equal to QVB. And so now I'm going to use my right hand to try and figure out which way the field points. So here's my hand. I'm moving it in the direction of the charge, so to the right. And I want my thumb to be pointing down. Oh, so I'm twisting my hand, so now my thumb points down. The way that the magnetic field points is out of the page towards you. So it's coming out of the plane of the page. So the magnetic field is coming out towards you. Let's move on. Now, just like a single charge feels a force when moving through a magnetic field, a whole line of charges or a current will feel a force when moving through an electric field. We use the same right-hand rule, and we just use a slightly different equation, ILB, instead of QVB. Now, if you have a loop of wire in a magnetic field, it's the same as a straight wire. Just use your right-hand rule for every part of the loop. Okay. Go ahead and try the next problem. Pause your video while you try it. Okay, a square loop of wire, 0.3 meters on each side, carries a current of 2 amps, and it's located in a 0.05 Tesla magnetic field. Pointed to the right, I can see. The left side of the loop is aligned along and attached to a fixed axis. Okay, so this is like some sort of a connection to the loop. When the plane of the loop is parallel to the magnetic field, what is the torque exerted on the loop? Okay, first you should know that torque equals force times distance from the axis times the sine of theta. In this problem, don't worry about your sine of theta term. That's just going to be the sine of 90, which is 1. So I'm just looking at what's the force and what's the distance. Okay. This loop, this part of the loop is at the axis. So R is going to be 0 for this portion. So this portion has 0 torque. Just like, can you open a door by pushing the hinge? No. So there's no torque when you push on something when it's at the axis. On this section, I notice that the current is moving parallel to the magnetic field. Well, anytime the current is moving parallel to the magnetic field, the force is 0. We talked about that on the last page. And that's the same with this here. So this has 0 force because it's parallel. This has 0 force because it's parallel. This has 0 force because the distance is 0. So the only part of this loop that's going to give us a force is this part right here. So I'm going to put in to my equation ILB for the force, and I'm going to multiply it by the distance from the axis. So the current is 2 amps. L is the length of the wire. That's 0.3 meters. The magnetic field is 0.05 teslas. And the distance from the axis is 0.3. Okay, so when we multiply these things together, what is this going to give us? 0.3 and 0.3 is 0.09, times 2 is 0.18, times 0.05. What are we getting? What are we getting? I'm going to grab a calculator. Time out. Okay, time in. I've got my calculator. Probably should have been able to do this in my head, and I can actually. It's B. 0.009 Newton meters. That's our torque. Okay, so far in this review, what we've been talking about is that when charges move through magnetic fields, they feel a magnetic force. Now, in the second part of this review, we're going to be talking about how a moving charge, a current, actually creates a magnetic field. Okay. And the most simple case is when we just have a straight wire. When we have a straight wire, the magnetic field loops around that wire. If you want to find which way it loops, you use right-hand rule number 2. You stick your thumb in the direction of the wire, and your fingers curl around the wire in the direction of the magnetic field. Okay. If this is for conventional current, if you know which way the electrons are going, electrons are negative, you can use your left hand for that. But most of the time, if it's just standard current, you want to use your right hand. The equation for the magnetic field around a straight wire is given by Ampere's law here, mu naught I over 2 pi r. Mu naught is just a constant. You can find it on your sheet. R is the distance from the wire. Go ahead and try the next two problems. Pause your video while you try them. Okay, hopefully you were successful solving the next two problems. Let's go over them. A long straight wire is placed below a compass. When a large conventional current flows in the conductor as shown, so up, the north pole of the compass does what? Okay. First, I'm going to figure out which way does the magnetic field go from this wire. It loops around. I figure out the direction of the loop using my second right-hand rule, using my thumb and my fingers to curl around. So I know that it's looping around like this. One thing that you should know about a compass is that a compass will always point in the same direction as the magnetic field. So if we put the compass on top, the north will turn to the right. So the compass needle will turn this way because that's the direction of the magnetic field on top of the wire. North will point this way. So it points to the north pole of the compass will point to the east. Again, compasses point in the direction of the magnetic field. Okay, now we have two long straight wires, each carrying a current I, shown above. Which of the following describes the forces on the wires and the resultant magnetic field at points along the dotted line? Okay. We're using right-hand rule number 2. I'm going to color code my wires. I'm going to call the bottom wire red. Hope you can see that that's red. And I'm going to call the top wire blue. Starting with the red wire, I'm going to point my thumb in the direction of the current, and my fingers show me the direction of the magnetic field. It's coming out of the page above the wire. I'm just going to keep drawing it out of the page everywhere above the red wire, and it's going into the page below the wire. Okay, I've taken care of my red wire. Now I'm going to look at the blue wire. The blue wire is also going to the right. So same idea. Above the wire, it's coming out of the page. And below the wire, it's going into the page. Keep drawing those X's below the wire. Okay, now I can answer the question. On this midway line, I hope that you can see from my picture that the X's from the top wire, which means field going in, are overlapping with the O's from the bottom wire, which is field coming out. Those will cancel, and along this line, the magnetic field will be 0. So I've eliminated it to B, C, and E. And now I want to know, will they attract or repel? So this, you're actually going to go back to force on a current carrying wire. Use your first right-hand rule. So I'm going to use it for the red one. The red one has a current going to the right. Has a current going to the right. And the magnetic field it's in is going into the page. So I point my fingers down into the page, and the force on the red wire is up. So the red wire is being forced up. I could go through that whole process again, but because of Newton's third law, if the red wire is forced up, the blue wire must be forced down, and the two wires therefore attract each other. You know, so right there, this is something that can save you a lot of time. Just remember, if you have two wires and the current is going in the same direction, they're going to attract. And if you have two wires and the current is going in the opposite directions, they are going to repel. You should be able to figure that out and work that out for yourself, but this can save you a little bit of time. When we're using the magnetic field of wires in applications, we usually make loops of wire. And loops of wire give the exact same magnetic field. Look at this. I'm going to put this next to it. Loops of wire give the same magnetic field as permanent magnets. You see that the loop, the current going in a loop here, look at the pattern. It's exactly the same as the pattern over here on our dipole. So right-hand rule number 3, you take your fingers this time and you curl them in the direction of the current, and your thumb tells you which way north is. So I'm getting north and south like this, and of course the magnetic field points away from the north as shown, and it points towards the south as shown. Go ahead and try the next problem. Pause your video now. Okay, you should have tried this problem. The magnetic field lines passing through point P inside the solenoid. A solenoid is just a loop, usually many loops of wire. We want to know which way is the magnetic field. So it shows me the current. I'm going to use my third right-hand rule. I curl my fingers around, my thumb is pointing up. So that means north is up here, south is down here. The magnetic field lines loop from north to south, and they go through the inside. They loop from north to south through the inside. So at point P, the magnetic field lines are up. They're directed upward. Okay, this is one of our last ideas in this unit. It's called magnetic flux. Flux is a simple idea. Anytime we have a magnetic field passing through a loop of wire, we have flux. And to calculate it, you just multiply the magnetic field and the area of the loop. If you have a bunch of coils, let's say you have 10 coils, you have 10 times more flux. Lenz's law says that nature hates a change in flux. Okay, nature does not want to change how much flux it has. So it will induce, this loop will induce its own current to cancel out the changing flux. Well, if there's an induced current, there must be a voltage. And the way that we find that voltage is with this equation, the EMF, or the voltage, same thing, is equal to the change in flux over the change in time. I like to rewrite change in flux as BA final minus BA initial over the time. And then there's a special case. If you have a rectangular loop that's moving into or out of a magnetic field, you can go straight to this equation, BLV. But make sure the L that you use is the length of the rectangular loop that's always inside the field. So if this is my rectangular loop, and it's going into, saying it's going into a field, speed V, the length that I want to use is this side here. This is L, the side that's always in or always out of the field. Go ahead and try the last problem. Pause your video now. Okay, I hope you were successful at figuring out this last problem. Let's take a look at it. A square loop, each side is 0.5 meters, and we know the resistance. It's located in a magnetic field of 0.4 teslas, directed out of the page, shown by those little O's. The magnitude of the field is decreased to 0 in 2 seconds. We want to know what's the magnitude of the current and what's the direction of the current. So first, the direction is very easy. This, the flux is coming out of the page, but then all of a sudden, over 2 seconds, the flux goes to 0. Nature hates a change in flux. It does not want to lose its O's. So what this loop is going to do is it's going to make its own O's by inducing a current. So O's are coming out of the page. It's going to induce a current to make O's, which is counterclockwise. So the current is going to go around counterclockwise like this. So it's either B or D. Next, we need to figure out what the current is. So I'm going to use Ohm's law. I equals V over R. I know the resistance. They gave that to me. It's 1 times 10 to the negative 2 ohms. But they did not tell me the voltage yet. So I'm going to find the voltage. I know that voltage equals change in flux over change in time. And I can rewrite that as flux final minus flux initial over time. The final flux is 0 because we turn the field off. The initial flux is simply the magnetic field, which is 0.4 teslas, times the area. This is a square. So the area is going to be the sides squared, so 0.5 squared, and the time is 2 seconds. Okay, multiply these, divide here, I get 0.2, 0.5 squared is 0.025. That's going to be something like 0.005, I believe. 0.025 times 0.2. Yeah, 0.005 volts. That's my voltage. Now I can plug that into Ohm's law. So that's 5 times 10 to the negative 123. Divide. The current is going to be 5 times 10 to the negative 1 power, which is 0.5. Uh-oh. I made a mistake somewhere, and I'm not sure where. Got my correct resistance. I must have made a mistake here. So let me double check real quick. The magnetic field is 0.4. Did I mess up the area? What's 0.5 squared? 0.25. Oops. So 0.25. I'm just off by a factor of 10 here. That gives me a voltage of 0.05. So that's 5 times 10 to the negative second power. Okay, good. And that gives me an answer of 5 amps. 5 amps. Choice B.